So I told you that decarboxylation occurs when you have H3O plus and heat. The H3O plus first does what to the esters? Not oxidizes. Hydrolyzes the esters, giving us what functional groups? Yeah, in this case, because we have this ethyl malonic ester, the functional groups that we get are two esters. But if we had the acetoacetic ester, then we would have a ketone and a carboxylic acid. I said that wrong just before. Here it hydrolyzes two carboxylic acids. Our other common use here, we get ketone and a carboxylic acid. That's what they want here. They want the hydrolysis product. Then you can see that they have H2O heat and loss of CO2. So this is where they want you to draw the decarboxylation product.
Yeah, that confuses me because I'm like, well, they have H3O plus heat already gives you the cleavage and the one carboxylic acid or ketone, whatever.
But there must be a part of you that can make sense of it too, because it doesn't form a carboxylic acid as decarboxylation is happening. It forms a carboxylic acid, and then decarboxylation happens.
Right.
I agree.
They didn't say anything like, oh, what's the intermediate or...
I agree. They should have said hydrolyzed intermediate here. The only thing that gives it away, though, is that in this second step, they give you this. I can't even zoom in on this page. They give you this minus CO2.
That confuses me more. What does that mean, minus CO2?
CO2 is lost in that step.
Right, but I'm like, I haven't seen any reagents that has minus CO2 or whatever.
Well, it's not a reagent.
Right, but
It's not.
they're not, they could say, like, forget the CO2 or...
Okay, so I agree. I don't show stuff like that in class very often. If I were to show something in class like that, rather than putting it over the reaction arrow, what I almost always do is have some sort of side arrow. So I'd have my beta carbonyl acid, and I might show CO2 coming off of this. I also don't like putting it over the arrow, but because it's here, let me show you this Nature Communications paper where they have reported for the first time the synthesis of methane tetrol. That is one carbon with 4 alcohols attached to it. And look at their reaction schematic. They start with CO2 and water. And from CO2, they add a hydrogen radical. And from water, they what? Lose a hydrogen radical. So over the reaction arrow, what is the reagent? Less hydrogen radical. That's weird. I agree. But it isn't uncommon. So hopefully this now just is a learning opportunity for you to see that some people will tell you what is being lost over the reaction arrow. If you continue further down, over here it gives you methane triol, which was only just reported last year, I think. And then they say less a hydroxide radical.
So it's fairly common to see it? I've never seen it before.
I don't think I would say it's fairly common, but it's not unheard of. Yeah. And I'm not a big fan of it. I would rather not put minus H2O. We could say something like that when we synthesize anhydrides. We could say, I'm going to use P2O5, my dehydrating reagent, and I'm going to lose water in the process. And so I can say less H2O. That's weird though, especially since P2O5 is actually chemically bonding with the water. So it's not even that water is disappearing, it's being abstracted. Not unheard of, for sure. Not something you'll see from me, for sure. Okay. Great question. Do you guys have other questions? All right. Tell me the reaction that we were introduced to yesterday, towards the end of our lecture. Aldol. And I kind of gave you a way of remembering what aldol is. Do you remember what aldol is kind of a combination of?
Yeah, it looks kind of like acyl addition.
It does look like acyl addition, true. But in terms of the name aldol, what does aldol mean? Sound it out. Aldehyde. Alcohol. So our idea for the aldol was if you started with this aldehyde and you reacted two equivalences of it with a base, like hydroxide, the product you get is an aldol addition product. It's an aldehyde alcohol, a beta hydroxy carbonyl. It's a bit confusing though because aldehydes aren't the only compounds that go through aldol addition reactions. Ketones can go through aldol addition reactions too. So what I would encourage you to think of is the aldol reaction relates to aldehydes and ketones. Remember that those are kind of distinct carbonyls from all of the other carbonyls, like acid chlorides, esters, anhydrides, carboxylic acids, amides, nitriles. Those are all the carboxylic acid derivatives. These two are not the carboxylic acid derivatives. So they stand alone. And then we saw that however you want to take an aldehyde and react it with itself to give an aldol addition, go for it. Take whatever base you want to use. Aldehydes only have one position that they can be deprotonated from and become a nucleophile at. Ketones, on the other hand, often have two positions, a more substituted and a less substituted. So we saw two different things that we could go with here. A small base, which is going to give us the thermodynamic nucleophile, and gives us an aldol addition. Yeah. It's just easy, sketch it out. It gives us an aldol addition from the more substituted alpha position. So I want to tell you what I did just to take those two equivalences of 2-butanone and fix them together. What I made sure to do was bond the alpha carbon of my carbonyl to the beta hydroxy carbon, because the beta hydroxy carbon was the carbonyl carbon of the second equivalence. And then I just made sure that I had all of my other groups. This beta carbon that gets attacked, it should have a methyl and an ethyl attached to it. And this alpha carbon that attacks, it should have the ketone and a methyl group connected to it. Then we said that if I take half an equivalence of LDA, I'll turn half of my ketone into the kinetic enolate, and it will be able to attack the other half of the ketone that have not been turned into an enolate. Do you guys remember why I don't have to specify equivalences with the thermodynamic base? This might be a good time to review your notes where we talked about acidity and bases. Why is it that I can get the aldol product without mentioning equivalences of my thermodynamic base?
Stable.
Not necessarily. It is a more stable nucleophile, a more stable enolate that forms, but how come I don't need to say half an equivalence here? If I want 1 part enolate to attack 1 part carbonyl. How good is hydroxide or methoxide at making an enolate from this ketone in solution? How good is LDA at making an enolate from this ketone in solution?
Was like 99%.
For which one?
LDA.
LDA takes that ketone and makes more than 99% of it into an enolate. That's basically complete enolization. Every single molecule of ketone is now an enolate. I don't want every single molecule of ketone to be an enolate. I want half of them to be enolates and half of them to be electrophiles that can be attacked by acyl addition. But what about this? How good is this at making an enolate? Not good. This one makes less than 10% enolate in solution. So for every molecule of enolate that forms from hydroxide, there's 9 other molecules of carbonyl that can still be attacked. So I'm able to get that product. It doesn't matter what the equivalence is. Now that was the aldol addition. I apologize for not clarifying that super well. But let's look at the aldol condensation as well. When you guys hear condensation, what do you think? What comes to mind?
Gas to liquid.
Gas to liquid. A gas condenses into a liquid. So you get a droplet of something that you didn't have before. And that's the idea here with condensation. Something is going to condense out of the reaction. A small molecule is produced. In this case, we're going to see water condense out. All right, our generic reaction here once again, I want to try and set this up so that you can see the two equivalences that are reacting with each other. Here's the weird thing. The reagents that give us aldol addition can also give us aldol condensation. It's just that it typically requires a little bit more heat. So, during the process of this reaction, an enolate forms, attacks a carbonyl, gives an aldol addition product. But after the aldol addition product, the base continues to react with the beta hydroxycarbonyl, and it condenses out a molecule of water, and it leaves us with this product. What is the functionality of that compound? What could we call that?
alane.
There is an alkene. There's and a ketone.
Oh, yeah.
A ketylene? No, I think what you're maybe looking for is enone, but that's not the functional group that we introduced last week. That would just be its suffixes. I'd be okay with calling it an enone, to be honest. But there is better description, actually, about this enone. Better relationship between proximity and the structure of the alkene and the ketone. What did we call it?
The conjugated carbonyl.
True, we had two names for it. One of them was a conjugated carbonyl. Because that ketone, or if R is an aldehyde, a hydrogen, then it's a conjugated aldehyde. It's conjugated through the pi system. What else did we call it?
Alpha beta unsaturated carbonyl.
Alpha beta unsaturated carbonyl. Now, in my opinion, conjugated carbonyl is not very distinctive enough because you can be conjugated with a lot of different things. But if you have an alpha beta unsaturated carbonyl, now you know it's just a ketone with an alkene, excuse me. So there is, I want to make this clear, there is an aldol intermediate that forms an aldol addition intermediate, which then continues to react to give the alpha beta unsaturated carbonyl. So what other product is not shown? I want to remind you guys that we saw yesterday that the base acts as a catalyst. Hydroxide here catalyzes the aldol addition. The base will continue to catalyze the aldol condensation. But what other product is missing? Look at the stoichiometry. Hydrogen leaves the alpha carbon in order for the alpha carbon to make a new bond. And the CO double bond breaks, so that hydrogen is transferred to the oxygen of the second equivalence. Now, the alpha hydrogen goes from CH2 to CH, and the beta carbon that was beta hydroxy loses its OH. I've lost an equivalence of H and OH. H2O is condensed out of the molecule.
Should there be a methyl attached to the same place as the OH in the intermediate?
Thank you so much, Sam. Good catch. Do you guys see what she's saying? I'm missing a methyl group once again. I did this yesterday too. So remember that this is the carbonyl carbon we see in the product. This is the alpha carbon. This is the beta carbon that we see in the product. The beta carbon is attached to R and methyl. But I don't have that methyl group down here. That methyl group needs to be there in the aldol addition. That's what I missed yesterday. And that methyl group in my generic example, that methyl group is also attached here in the alkene, where that beta carbon is. Totally my fault. Thank you. So there is a limitation on this. In order for aldol condensation to occur, the alpha carbon has to have at least 2 hydrogens that can leave. The beta carbon starts as a carbonyl and ends as an alkene. That might feel similar to the Wittig reaction. If you guys remember, we took a carbonyl and an ylide and we metathesized an alkene out of them. Kind of similar here, where we take an alpha carbon and a carbonyl and we methathesize an alkene. We make an alkene out of carbonyls. Okay, now just for a side reaction, this is not something that we're going to cover much, In acidic conditions, the aldol addition cannot be isolated. The aldol addition intermediate, or the aldol addition product, intermediate is a better word for it there. So if you are to use H2O and H3O plus in this reaction, you don't need heat as much as you do here with the base, and you can't isolate that aldol addition intermediate. The acid continues to catalyze the reaction all the way down to the condensation. We're going to look mostly in basic conditions, but I want you guys to recognize that this reaction can run in acidic conditions too. So let's do some examples. Let's take two equivalences of this butanal. I'm going to switch it up a little bit. Instead of hydroxide, we'll just use a different small base. What I like to do in predicting these structures is to actually start with the alpha-beta double bond conjugated to the carbonyl. I know that I've set this up in a different conformation than we had over here. In fact, there might be a better way that I could give this conformation, or a better conformation for me to give for this product. A conformation which, Sam, you might agree, is much easier to keep track of that methyl group and not lose it. Because if you look at this conformation, all you're really doing is connecting the alpha and beta carbons together. Here's alpha, here's beta. You're taking that carbonyl and you're just making it into an alkene. So I like to start there when I am predicting a product. I start by drawing that alpha-beta double bond that forms. And then I go and I make sure that alpha is connected to everything else that alpha needs to be connected to, and I make sure that beta is connected to everything else that beta needs to be connected to. Here's alpha, here's beta. Alpha needs to have 1, 2 carbons coming off of it, 1, 2. Beta needs to have 1, 2, 3 carbons coming off of it. 1, 2, 3. That's just two equivalences of that aldehyde slid right underneath each other so that alpha and beta can connect into that ketone. And really, you could do that same thing for making the aldol addition product. Take two equivalences, slide them underneath each other, make an alpha-beta bond. In this second example, what I want you guys to give me is what compounds come together to give me this conjugated carbonyl. I want you to retrosynthesize this product. Okay, yeah, it's drawn a little odd, but it is right.
I know you're gonna say that.
Yeah, good job. Great. Yeah. Good. Hey, can you put words to what you did in order to predict that?
I separated both compounds and then put oxygen on the double bond.
You did what? Sorry?
Separated both compounds
Separated them.
and then put oxygen on the double bond.
Okay. So if you take the product and you just rewrite it, then all you have to do is erase that alpha beta double bond and slap an oxygen onto the beta carbon. So in retrosynthesis, this is what I want you guys to think of. For both aldol and addition and condensation, break the alpha beta bond. Whether that's an alpha beta single bond to the beta hydroxy carbonyl or an alpha beta double bond to the conjugated carbonyl. Give the hydrogens back to alpha. In the case of aldol addition, one hydrogen goes back to alpha. In the case of aldol condensation, two hydrogens go back to alpha. And beta becomes a carbonyl. Always. The beta hydroxy was a carbonyl. The beta alkene was a carbonyl. 3 steps to retrosynthesize these. That's all you have to do. Now let's look at example 3. Where I want to synthesize I did it a little short. I want to synthesize this conjugated carbonyl. Is it the same starting material as before? One phenyl acetone or one phenyl propanone. There's really no other place it could be. How do I make the alpha carbon nucleophilic at the less substituted alpha carbon?
Acidic conditions?
No, not acidic. Because enols in both acidic and basic conditions prefer to form the most substituted enol. I need this enolate to be the least substituted.
Use LDA.
I could use LDA. Now, if you remember yesterday, when we used LDA at half an equivalence, that gave us an aldol addition that ended with O minus. Because there's no proton source. There's nothing that we can use to protonate the beta hydroxy alcohol. So we added H3O plus afterwards to protonate things. What I could do here is follow LDA with water and base and heat. Because LDA will give me the aldol addition product, and then by adding in base and heat, I can drive the aldol addition product down to the aldol condensation. Or, like we mentioned here, acidic conditions, very challenging to isolate that intermediate. So instead of just neutralizing everything, I didn't mean to put that line through there as if to say that's not good. I just meant to say, or we could add acid and heat because we can do more than just neutralize it. We can make the conditions truly acidic. And we know that in acidic conditions, that aldol addition product will react down to the aldol condensation product. Two ways to do that. But you have to first start with LDA, and LDA isn't a catalyst like hydroxide or methoxide. LDA has to be followed up with something else. So we can control the regiochemistry, but then we have to do a little bit more work. All right, any questions on that? Then it is time for the mechanism. Ready? Let's work with one of those two examples because it's less likely that I'm going to have you work with LDA. 99.9% chance I have you work with hydroxide or methoxide, something like that. So tell me which of those two examples you'd like to see the mechanism for. Did we do a ketone yesterday or an aldehyde? All right, let's do a ketone then. Now I'm going to draw both equivalences of my ketone out, even though only one of them will be utilized in the first step. And the small base that I'm using, oh, it is hydroxide, but it could be any small base. I'm explicitly showing one of the alpha hydrogens. I don't need to show both of them because only one will be deprotonated. And I'm going to the more substituted position because I have a thermodynamic base. And I can see in the product, my nucleophile needs to form at the more substituted alpha carbon. Hydroxide deprotonates the alpha position, forms the most substituted enolate and water. Now we could show the resonance form of this enolate like we did yesterday, but this mechanism already contains more steps. So oftentimes on mechanisms where you are asked to show this, I will be explicit about saying show all resonance forms or not needing to show all resonance forms. It is your job to read those instructions and make sure that you look for showing the resonance forms of the enolates if you need to. I'm not going to do it here, but if you want to draw the resonance form, have at it. There's absolutely nothing wrong with adding it if it's not required. But there is a problem with not showing it if it is asked for. So, enolate attacks from the alpha position to the carbonyl. That's my electrophile. And I'm going to continue drawing this up here. All right, now this is where things can get a little messy, which is why I like to stack these molecules like I have. I've got my carbonyl, which has just reformed. Alpha is forming a new bond. If it helps you, just elongate these bonds, exaggerate them so that you can connect them in a way that makes sense. Alpha attacks beta. Beta has methyl, CH2 phenyl, and now the beta carbon also has O minus. I've redrawn water, explicitly showing an OH bond because the next step is protonation. O minus gets protonated by water and gives me my aldol addition intermediate. Now I've added my second alpha hydrogen. It was there the whole time, agreed? That alpha hydrogen was always there. It just wasn't relevant until now. Because look at the product. Both of those two alpha hydrogens are gone. Now that I've formed my aldol addition product, hydroxide deprotonates my second alpha hydrogen. I'm going to show this once again, forming the enolate in its most stable form. You could show it in its less stable form. It actually doesn't matter what form you show an enolate in. Unless it's asked for you to show it in both forms, in which case, then it matters that you show it in both forms. Do you see this molecule of water on the board? That is the condensation. That is the water that is produced in this reaction. That water, unlike this water, that water is not going to continue reacting. Do you guys see what needs to happen to get from this intermediate to the final product? Tell me some things that need to happen.
Deprotonation.
I don't agree. No, I don't see how deprotonation gets us to that. Okay, keep going. An elimination needs to happen? Okay, tell me what bonds need to form, and tell me what bonds need to break.
The alcohol one needs to leave.
The OH needs to leave. There is no CO bond at that beta position. So the CO bond needs to break. What else?
So protonation.
No, there's no hydrogens that need to be added from here to get to that final product. So no protonation needs to happen. Okay, but tell me what bonds need to break and tell me what bonds need to form. The CO bond needs to break here.
Yeah.
What else?
The double bond.
The CO double bond needs to form. Okay, what else?
The OH. You said the CO bond needs to break.
That needs to break because it's not there in the final product.
Right.
What else?
Double bond.
This alpha beta carbon-carbon double bond needs to form. What else? There's one last thing.
The new CO bond, the double bond with the other.
Yep, you gave that to me already. This bond needs to break. This double bond needs to form. This double bond needs to form.
The hydrogen has to.
Hydrogen won't be involved at all, but Caesar?
That other double bond between the carbonyl and that
Needs to break. 4 arrows we're going to see here. Oxygen to the CO double bond. Not 4 arrows. I apologize. 3 arrows. CC double bond. Those pi electrons move down to form a different CC double bond. And then the CO bond breaks. Every time a bond breaks, it breaks to the more electronegative atom. Oxygen takes those electrons. What I'm trying to demonstrate to you guys is that if you can get to any point in a mechanism, you should be able to try and reason your way to what needs to happen next just by comparing it to the final product. You know what you need to get, what needs to happen. There's one more thing that's produced in this step. Can you tell me what it is? Hydroxide. And hydroxide was what exactly? That was my catalyst. So hydroxide has regenerated. My catalyst is truly a catalyst. And here, a molecule of water is produced by the reaction, condensed out of the structure. I want you guys to notice something very strange. In OChem 1, you're told that alcohols are never a good leaving group unless you can protonate them and turn them into water, and then they can be a good leaving group. But do you notice what we just kicked off here? An alcohol. That's very strange. This is maybe the only time that you really see that happen in organic chemistry. All right, any questions on the aldol condensation? All right. There is a different type of reaction involving aldol reactions. This is what we call the crossed aldol reaction. This happens when you take two different carbonyls and you want them to react with each other in a selective way. So let's say that I have a carbonyl with R prime and a carbonyl with R double prime. And I react these with hydroxide. I get 4 different products that can occur. One, where the carbonyl with R double prime acts as the nucleophile, and the carbonyl with R prime acts as the electrophile, or one where R prime attacks R prime, or one where R prime attacks R double prime, or one where R double prime attacks R double prime. I do want you guys to recognize that these are the crossed aldol addition products, and you get something incredibly similar when you have the crossed aldol condensation products. Should we go through and show what the 4 crossed aldol condensation products look like as well? R prime is attacked by R double prime. R prime is attacked by R prime. R double prime is attacked by R prime, and R double prime is attacked by R double prime. Not great, right? So if I wanted to take two different carbonyls and mix them together to make an aldol condensation product, how would I know which of those four products I'm going to make? Do I make all four of them? Which one yields the largest? How can I avoid getting a mixture of four different structural isomers? How can I prioritize just one? We can control the reactivity. We can make some limitations to this.
Does this apply to this condensation? No, this is addition.
It's both. Do you see how next to each blue compound is a red compound that has it has the same R prime, R double primes?
Okay. So you could do it either one.
Correct. So if we want to try and control our product, what we need to do is limit the reactivity. And that means we can minimize alpha hydrogens. For instance, in this crossed aldol reaction, only one of the aldehydes can become a nucleophile. Benzaldehyde on the left can only, excuse me, I said that incredibly wrong. Benzaldehyde on the left can only be an electrophile. This is an electrophile only. Benzaldehyde has no alpha hydrogens that it can use to attack or be turned into an enolate. And on the right, where I mistook it again, acetaldehyde can be an electrophile, but it is the only nucleophile present. So you might still get some crossed products. You might get acetaldehyde attacks acetaldehyde, and acetaldehyde attacks benzaldehyde. But you've limited the reactivity from 4 products to just 2. You can do something like limiting alpha hydrogens and also making one of the compounds a much better electrophile. What is a better electrophile, an aldehyde or a ketone? Which is a better electrophile, aldehyde or ketone? Which accepts electrons more easily? Ketone? No.
Aldehyde.
Ketones have more steric strain and more induction because they've got larger carbon groups pushing electron density towards that carbonyl carbon. So the ketone is less of an electrophile. The aldehyde is more of an electrophile. So this is the best electrophile. That means it's most likely going to be the one that gets attacked. In fact, I'm sorry, I want to make another change. I don't want this to be propanal like I have it, because propanal is more acidic than 2-butanone. It has a lower pKa, and propanal has alpha hydrogens. So let's actually turn this into 2,2-dimethyl propanal. We're going to stick that tert-butyl group on there. I think you guys would agree that's basically like having it be an aromatic ring. There's just no alpha hydrogens at that position anymore.
Mm-hmm.
So this is the best electrophile, and once again, this is the only nucleophile that can form. So I can only form one nucleophile, and I've got one compound that is the best electrophile. This is going to have one major product. Maybe some impurities, but almost every reaction has some impurity. The third, and in my opinion, most surefire way to limit the reactivity introduce an enolate directly. Don't worry about whether you're going to get 2 different products, 4 different products. Make sure that one of them is already only an enolate and have the other one be an electrophile as a carbonyl. So here's an example where I do have the capacity to form a nucleophile. But I'll react this exclusively with this enolate. Exactly. This must be the nucleophile, and this must be the electrophile. Now, I haven't maybe added enough detail for you guys. I do want to clarify something. In these first 2 reactions, you're still going to end up adding a base. That's what we saw here. When I add a base in these cross-aldol reactions, I can get a mixture of different products, and I can minimize which one has alpha hydrogens. I can make one of them a better electrophile, or I can introduce an enolate directly. I don't need a base here. Once I take that enolate and mix it in with my carbonyl, they just react. I don't need a base to generate the carbonyl. So then the question in your minds should be, why didn't we just do that with all of them? And you can, because like I said, this is the best way. But how do you make that enolate? Where does it come from? Well, we know that enolates come from carbonyls. Yep. So there's the ketone that I would use. And do I just mix hydroxide with it before I add it to the other carbonyl? Because hydroxide is just going to give me aldol addition with that ketone. I need a base that will turn it into an enolate completely and not allow it to react with neighboring molecules of itself. LDA. And this time I want it in one equivalence. I want a stoichiometric, maybe even an excess amount of LDA, so that 100% of that ketone is introduced to the reaction as an enolate, or at least greater than 99%. What do you think? Good. Okay. Let's do a couple of practice problems. And if you guys need to take a minute to get up and move around and get your blood flowing, now's the time to do it while I put these up on the board. And this would be a good first step, but you might want to follow it with something else. Sure.
Sure. Is that not the best?
Maybe not the best, correct.
On which one?
On that second one.
The second one?
Sorry. The top one does work.
Okay.
And if you want, oh no, the top one does not work.
Okay.
Your structure is close on the top one, but it's not quite there. Okay, so this is the right structure, but how can we make sure that it's going to attack from the correct position? So what I would do is either show reagents that you would need to add with it, or show its enolate form before that. This is okay, but it's not the best. This is great. good. That's a good way of doing it. Yeah. Good. But now we need to find a way to make sure that it reacts with the regiochemistry that we want. This is good, but it really requires a 1 and 2. You're saying that they mix together. This is not accurate, but you're on the right track. Okay, good. No, that's it. But this is not accurate. You've got your structures swapped. This is okay, but it's not the best. And I forget what I said up here, but you got the right structure, but you need to show how it's going to react from the position that it does. It's got 2 alpha hydrogens, so how will you control its regiochemistry? Or you could show it in the enolate form that is required for it to react. Mm-hmm. Yeah, that's a great way to do it.
Better.
Mm-hmm. Yeah, that's great. Actually, the other way would work, and I'll explain why in a minute.
Mm-hmm.
This is also good if you can, if you want to, show how you make it similar to this.
Okay.
And what do you have down here?
I have it finished.
Okay, but this is
Working on it.
Mm-hmm. Yeah, think about what is the nucleophile and what will be the electrophile. Mm-hmm. Okay. Think about what's the nucleophile, what's the electrophile, and where that bond will form. If it helps, label your alpha and beta positions. Try to predict what your structures look like. I can only give you guys a couple more minutes and then we'll have to move on. Yeah, there you go. These maybe weren't the best examples either. I can see a couple of things in them that I wasn't fully intending by drawing those structures, but good.
So I just know that the enolate would be the carbonyl, right? So that means the alpha.
Mm-hmm. That's it. Do you guys want to put anything up on the board?
Sure. Just click on.
Yeah. Caitlin, there's a blue marker up there if you want to.
Oh, I didn't even see that third one up there.
Oh, well.
Let me click on.
So you do have an alpha beta unsaturated carbonyl, but your carbonyl is actually the electrophile. So that's going to become beta of the alpha beta unsaturated. Meanwhile, this of your enolate, this is your alpha. Alpha attacks beta. Alpha beta double bond. This is your carbonyl product. Nice. All right, guys, we're going to have to go through them together. So with the top one, we're making an aldol condensation product. The regiochemistry is less substituted, but I made kind of a small mistake here in what I planned to do. The reagent that is missing has this structure. And you can see that it has 2 hydrogens that can be removed from the left and only 1 alpha hydrogen that can be removed from the right, which means the carbon on the right can never form a condensation product. The alpha carbon on the right is more acidic, but can only lead to an aldol addition because it doesn't have a second hydrogen that can be deprotonated. So if you added HO minus here and heat, yeah, this is the only condensation product that you can make. But there would be a better way to set this up, which would be to say, have this ketone with LDA, or in other words, have this enolate add. But then, if you're adding LDA, you're also going to need to finish it off with more base and heat, or you're going to need to add some acid and heat. So I feel like I tricked you a little bit with that one. And then it's actually the same situation down here, where we take this ketone and we form an alpha-beta unsaturated carbonyl, but only one of its 2 alpha positions can do condensation because only one of its 2 positions has 2 hydrogens that can be removed. So if you said hydroxide and heat, that is the only condensation product you could form. But it would be better to say add LDA at half an equivalence and then follow it up with acid and heat to drive the condensation step. So I would have accepted hydroxide and heat. Probably the best method would be this. Here we see that this ketone reacts with LDA and gives us this enolate. Doesn't matter which side you drew it from because it's equally substituted, so you get the same enolate. Then we introduce that enolate to this cyclopropyl carbaldehyde. This is my alpha carbon, this is my beta carbon, so my product should have alpha beta unsaturated carbonyl. I got a couple of answers for this one, where the cyclopropyl carbaldehyde was the aldehyde that remained, rather than the aldehyde or the carbonyl that was attacked. This carbon needs to be attacked, needs to become the beta of the conjugate carbonyl. One thing that I tried to clarify here was to give me the aldol condensation product, because it can be really challenging to know all the time since the reagents are very similar. Are you looking for aldol addition or are you looking for aldol condensation?
I have a question back up at this other one. Are you saying you'd need those things if you didn't add the LDA, or like which? Because I thought if you added the LDA and just had the enolate, then you just didn't need the base.
Okay, so here, yeah.
Yes.
If you turn this into an enolate with LDA, it attacks and gives an aldol addition product that can't be protonated. It just is
Okay.
O minus.
Okay, so just to get to the aldol condensation.
Yeah.
Okay.
So then in order for it to continue reacting, you need to continue adding things.
All these auto condensation, right?
They are, and I didn't think about that either. So I apologize. Now in this last one, I really like this because this is a very simple molecule. It's a very simple conjugate carbonyl. Maybe the only thing that's more simple than this conjugated carbonyl is this conjugated carbonyl, where it's an aldehyde instead of a ketone. And the retrosynthesis works all the same. Take alpha and beta, separate them from each other. Beta is a carbonyl. That's formaldehyde. Alpha gets 2 hydrogens back. That's acetone. If I were looking at it here, I would also have formaldehyde and acetaldehyde. And conveniently, since this is the only nucleophile and this is the best electrophile, hydroxide does work to give me this as a major product. But another way that we could do this is to simply react it with LDA, because there's only one alpha hydrogen position that can be eliminated, turned into a nucleophile. Only one thing that will act as an electrophile then. All right. What do you guys feel? Cool reactions, bit of complicated structures. Next, I want to look at the Claisen condensation reactions. Aldol covers ketones and aldehydes. Claisen covers esters. You guys might remember that we talked about esters at the beginning of this unit, and then we haven't come back to looking at esters as enolates yet. So here's our generic example. If I have an ester, let's say that it has ester linkage OR, and then it has a CH2R prime. Doesn't quite matter what that CH2R prime is. And to be quite fair, as long as there's one hydrogen here, this reaction works. I'll need two equivalences of my ester, and I react it in basic conditions. This time it is crucial that the base matches the ester linkage. Because this is a condensation reaction, there is no Claisen addition product. There is an acyl addition intermediate, kind of, a tetrahedral intermediate, but it condenses out a molecule of water. So here's how I like to draw this. Start by redrawing the left-hand side of the ester. And then connect this carbonyl carbon to an actual ester. And that ester also has R prime coming off of its alpha position. What is the functionality of that compound? Don't be shy. What's the functionality? I introduced new functional groups to you guys last week.
Oh,
Which functional group is this?
Beta keto ester carbonyl.
That's it. Beta keto ester. Bit of a misnomer because it could also be an aldehyde. It doesn't have to be a ketone, but it is commonly a ketone. Yeah, you could call it 3-oxoester. Beta carbonyl ester. Beta carbonyl. I've made that mistake in the past where I've introduced this only as beta keto, and then I show an aldehyde product, and they're like, that's not beta keto. Yeah, and aldol doesn't need aldehydes, so. All right, let's look at some examples. Example 1. Let's take ethyl acetate, 2 equivalences, and let's react it with ethoxide. I'm going to start by drawing the simplest form of the product. Beta carbonyl ester. Excuse me. Oh, I didn't show you guys. There was a condensation product. Excuse me. What is missing stoichiometrically in the generic reaction? Second equivalence of OR. I have two equivalences of ester, but I only have one equivalence of ester in the product. Not to mention, I had an alpha hydrogen that is gone. So the alpha hydrogen is missing. So here's the simplest form. That's a beta carbonyl ester. I know my ester linkage is ethyl. I need to figure out what else is coming off of the beta carbonyl carbon. Well, that's just whatever was coming off of the carbonyl carbon, which in this case is just a CH3. And then I need to figure out what else should be attached to the alpha carbon, but in this case, there is nothing else attached. R prime in this case, just be hydrogen. So this is my product. Do you know what that compound is? Do you recognize it from looking at pKa's last week and looking at alpha alkylations this week? Is that this week? What is that compound? Okay, I think back. Yeah. Ethyl acetoacetate. That's an acetoacetic ester. So here's an interesting thing about the chemistry, and we're not going to show it this way. We're going to assume aqueous workups, but I do want to clarify for you. When this product forms in the presence of a catalytic base, the alpha hydrogen is even more acidic than it was before. So if this forms, then it just readily becomes deprotonated to give us this enolate. That's not the product I want. The product that forms reacts with the base and gives me an enolate, and this is where we assume aqueous workups. We would add acid in order to actually generate this product. So a fun story about this, when I was in OChem 2, I had to show a mechanism for this reaction, and I lost points in my mechanism because I didn't show that in the final steps, the alpha carbon gets deprotonated and then has to be protonated to get the final product. And I went up to my professor and I was like, that's BS. I formed the right product. And then you wanted me to show that it unformed and then reformed again? And she said, well, that is what happens. It forms in the presence of a base. It's more acidic than it ever was. Its acidity is like 10 orders of magnitude more acidic than the precursor. And she said, yeah, you have to show that. I understand, but I probably won't be requiring that same level of fortitude when you have to show these mechanisms. I might not have you show these Claisen condensation mechanisms either, because they're actually fairly simple. Sorry? Yes, you should study it because it is well rounding, and it looks very similar to Aldol. All right, let's look at this. I'm going to abbreviate a few things here. I'm going to abbreviate the ethyl ester as OET. One of the alpha hydrogens gets deprotonated, and this gives me my ester enolate. Plus ethanol. My ester enolate attacks from the alpha position to the carbonyl. Acyl addition. Alpha attacks beta. Beta had a carbonyl and that ester linkage. Now beta has O minus and that same ester group. You guys see ethanol here in this second step? That's the equivalence of alcohol that condenses out of the molecule in this reaction. This product on the right, or this intermediate on the right, is considered a tetrahedral intermediate. Beta carbon started sp2. The beta carbon will end sp2. This is a tetrahedral intermediate of that carbon, at that carbon. O minus collapses, reforms the carbonyl. Something needs to break off. Carbon-carbon bonds, too strong to break. So the carbon-oxygen bond kicks off OET minus. I'm left with my beta keto ester and an equivalence of ethoxide, catalytic base. We could do the same thing, and all we have to do is diversify the alpha carbon. And then you've got two of the same R groups coming off of your structure. But we could also take this intermediate and we could use it to do alpha alkylation, and we could make the carbon chain that we want to from it. But then we get into the cross-Aldol reactions, crossed Claisen reactions. Now, in these reactions, it is important that the two esters share the same ester linkage, but it does not matter whether they share the same R groups at their alpha carbons. So I've got R prime, R double prime. How many different products can I make here? Yeah, the ester with R prime could attack the ester with R double prime. The ester with R prime could attack R prime. R double prime could attack R prime. R double prime could attack R prime. 4 possible products. So, what's the best way to limit this? Same thing. Limit the number of alpha hydrogens. so that only one compound can be a nucleophile. You can't really make one of them a better electrophile unless you've got formate. That's the aldehyde ester. But the best method is to just use LDA. So let's take this ester, 3-methyl 3-phenyl propanoate. And we can show this kind of as a multi-step synthesis. First, react it with LDA. That takes every molecule of ester, turns it into an enolate. Then, introduce whatever other ester you want to add. I want to add methyl formate, just for this example, because I think formate is cool. Remember that beta shows up on the left when we draw it this way? And beta is the ester that loses its ester group. Beta is the electrophile. Alpha, which attacks beta, all of its R group, it's easiest to draw it coming straight down from the beta keto ester. So here's how I'm going to draw my product. This is my beta carbonyl ester. My carbonyl is not a ketone anymore. My carbonyl is an aldehyde. And off of alpha, I have 1 phenyl. 1 carbon phenyl. And if I wanted to, I could hydrolyze the ester to a carboxylic acid and decarboxylate because I have a beta carbonyl acid at that point. One more time?
Never mind.
Okay.
I just thought that would be like the reverse reaction, but
No, if I did take this and I did H3O plus and heat to hydrolyze and decarboxylate, beta alpha 1 phenyl, beta alpha 1 phenyl. There's the structure I get left with. 3-phenyl propanal. Okay, there is another set of reactions that are difficult to name. So I'm going to call these the Aldol Claisen crossed reactions. Because I want you to think of aldol being aldehydes and ketones and Claisen being esters, but there is no reason that you can't take an aldehyde or ketone, make it a nucleophile to react with an ester, or take an ester and make it a nucleophile to react with an aldehyde or ketone. So let's take our ester as a nucleophile. Let's react it first with LDA to make it into an enolate. Then let's react it with formaldehyde in the presence of excess base and heat. That's going to drive an aldol condensation reaction. Just for reference, this will be alpha because it's reacting with the LDA to become a nucleophile. This will be beta. There's an aldol addition intermediate in there where the alpha carbon attacks formaldehyde and produces an alcohol, a beta hydroxy alcohol. But this is the aldol condensation. Actually, I do kind of want to show the aldol addition intermediate that forms. I think it's useful to see the beta hydroxy carbonyl in this form. There's the beta hydroxy intermediate that then gets reduced. All right, I've run out of time. What we'll do tomorrow is pick up with when aldehydes and ketones act as the nucleophiles on esters. And rather than making beta keto esters, what we can make is beta keto ketones or beta keto aldehydes. After we finish the crossed aldol Claisen reactions, we just need to look at Michael addition, conjugate addition, and the Robinson annulation, which are actually reactions we have seen before. So that's our last day of class. That's our last day of new material. Next week, Tuesday and Wednesday, is review days. So as you're preparing for your unit tests this weekend, also be preparing for the cumulative course review next week. All right? Okay. Take care, guys. I'll see you tomorrow.